Hi, everyone. Can you hear me?
Yes.
Okay, thank you. Uh, hello, everyone. My name is Marian. I work as a software architect at NVIDIA, Mellanox business unit. And today we are going to talk about our vision of a fully programmable Sonic switch and walk through the Sonic software stack to see what it takes to be able to extend all the layers without patching a single line of code. And even to my surprise, that there is very few things that need to be added to Sonic to be able to do that. So that's what I want to share with you today. So agenda for today. Motivation. We'll start with some rationale why we would want to see these capabilities in the Sonic switch. Example use case, something that presents a problem, and then I will walk through all of the software stack to see how this problem can be solved in a scalable way, and what benefits it provides. We will take a look at the general architecture overview for such extensions, and as I mentioned, we'll go over all the software layers, including SAI APIs, Redis RPC libraries, Sonic application extensions infrastructure that is right now in the works in the Sonic community. What is required from Work Agent? I will show you a short demo for this example and conclude with call for action. So motivation, I will start with the picture presented at the last OCP, because the motivation doesn't change. Today, Sonic is developed as one-size-fits-all distribution. If any extra functionality can get in, it will be only as a new Sonic-based distro, which makes it hard to maintain, and especially at proprietary features not intended to go mainstream. What I mean by that is it is often a case where you want to support something that is not really possible to be fully disclosed due to some intellectual property considerations and so on and so forth. But still, you want to enjoy all the benefits of the strong Sonic base that provides you all the layer 2 and layer 3 infrastructure, but extended with something very specific. So let's take a look at the example of a successful programmability support, Linux kernel. Today, Linux provides a full end-to-end support, where kernel has a standard network stack, whereas eBPF application is used for extra functionality. So it comes with a compiler support, native tools integration, etc. So here we have a very nice separation where we have you can take Linux kernel out of the box and run it with some of the popular distros, and then add some special logic, as was successfully proven to be working many times by adding different pieces like your own firewalling, connection tracking extensions, and so on and so forth. So this is something that I think we should follow, and I think that this is something that can be achieved in Sonic. So by following the same model, Sonic will be able to provide end-to-end programmability as well, where the divide will be pretty much the same. Base OS will be responsible for standard network stack, and we can take P4 programming language as a candidate for developing our extensions. And in between, we would need to ensure that we have an extendable architecture across all of the software layers, which we are going to explore next, for us to allow to compile our P4 application into a pretty much native Sonic application, Sonic control plane with all the following layers. So instead of talking about something too abstract, I think this talk will be better delivered with some examples. So this is something that I chose that is not necessarily as extreme as having a proprietary protocol running on Sonic, but this is something still understandable and relatable. So the problem that I want to discuss today is extending mirroring functionality in Sonic. So today Sonic supports packet mirroring to some extent with Everflow feature. We have ingress mirroring, we have egress mirroring. But the problem is that only predefined packet qualifiers can be matched to select packets for mirroring. And more so, Sonic has a fixed set of keys for the Everflow table from which we can choose from. So our goal here would be to program a new mirroring table into Sonic that will match on rocky fields. So our DMA is not defined in SAI and Sonic today, which makes it pretty much impossible to do any pipeline processing for the rocky packets. So, for example, I want to be more specific than just saying, please mirror packets destined to some host. I want to say that I would like to see not only the packets to that host, but also rocky packets that belong to that have a specific partition key in their BTH header. And I want to do that. I want to program this table in my ASIC with full Sonic integration by compiling a P4 application into SAI, RPC, and so on and so forth. So we will see how we can do that. And another challenge here is that new application will be able to reuse the existing mirror session. So as I mentioned, Sonic supports mirroring today. So we can create mirror session. We can define some mirroring rules today for example, IP TCP, IP UDP packets. I want to reuse the same session, but also include my own packet qualifiers to have a more fine control over what I'm mirroring for rocky packets. And to make it something that is valuable as a final solution, we have a requirement to not change or upgrade any of the standard containers, meaning that we will not touch syncd, SWSS, or anything else while deploying our application. So to achieve all of that, the proposed architecture or the template that could be used for such an extension looks like that. The idea is very simple. We want to pretty much replicate Sonic software stack in our extension. meaning that if we don't want to touch SCI in syncd, we don't want to touch SCI Redis in both syncd and SWSS, but we still want to patch them because we will update SCI APIs. Then we will just replicate another instance of our syncd and SCI and so on and so forth with patched headers and implementation, and see how it all can live together. So this is, I think, the model that should be followed. So let's see what in our example will be missing from Sonic today in order to achieve this goal. And as I mentioned, it's surprisingly few things that are still missing to be able to do that. Let's start bottom up. So Flex SCI, basically extending SCI. So SCI has a very good architecture today, and SCI APIs already support running multiple instances of libSCI. We have appropriate APIs for that. Also, we can extend SCI APIs by either manually adding new extensions to SCI/experimental/extensions.h, or we could also auto-generate them using a compiler. Like, for example, we have Flex SCI directory in our SCI repository that will allow us to auto-generate SCI extension APIs from a P4 code. So this is what we are going to use to make our life easier. And this is, as I said, everything today in SCI is in place and it works surprisingly well. But the problems arise when we go to higher layers. So syncd is actually also almost there in terms of multi-instance support. So here, going back to the diagram, you can see that we are running two instances of syncd. First one is the main one in the syncd container, and another one is the syncd instance in our extension container. So it's not only possible in Sonic to run multiple syncds for multi-ASIC systems, but we can do the same trick with small changes for the same ASIC, meaning that we will follow kind of a divide and conquer approach, where each instance will handle its own SCI objects, and to distinguish between the ownership of the SCI objects, every syncd instance that is not a main instance will subscribe to its own table different from ASIC state table to avoid conflicts with the main instance. For example, mirror session that I mentioned is created and kept in ASIC state table by the main instance, but our new table entries are created in ASIC state, for example, Rocky Everflow table. So this is how they will know what how to divide their work and who owns what. SCI Redis, same thing. It works well when only one consumer and producer, usually syncd or Kagent, is active. But when adding external instance entities like new syncd instance, producer applications problem arise because they keep internal state. So the RPC should allow for using object IDs even if the application did not create them. So this is what is missing basically from SCI Redis. In our example, it means that I should be able to use a mirror session created by main instance, although I didn't create it, but I still need to be able to reference it. And same thing, it should write to write ASICDB entries in its own table different from ASIC state to avoid conflicts. Control application that we need to develop. This is something up to the developer. It implements control app could be auto-generated if possible, if it is used by the controller, or could be written manually. The only consideration for such control application that is different from the org agent, so you can think of it as a distributed version of org agent. The only consideration that it needs to take when creating a switch, it needs to initialize the switch with attribute init switch set to false. Reason for that is that it's not main instance. Instance being org agent initializes with this attribute set to true. And we are saying that we are not the main one. We don't need to reset our ASIC. We are just connecting to it. So this is the main difference. Now talking about org agent, what do we need from it? Just the mirror session. So as I mentioned, org agent today already knows how to create a mirror session. We want to use it. So the requirement here is external applications should be able to use resources owned by org agent by having explicit appdb entries for them, for example, tunnel, mirror session, etc. And ideally also to org agent would provide a mapping from application DB to ASIC DB, so we could easily find those object IDs that we are interested in. And Sonic application extensions infrastructure, this is kind of the wrapping up everything that we have done so far. Just taking all our software layers, packaging them into a compatible Docker image. Everything should be from that point auto-generated to as much extent as possible, like UIs, CLI, REST API, and so on. Systemd service should be auto-generated, of course, and in the future, more of the hooks added in, like telemetry, logging, ISSU integration, and so on. So now what I want to share with you as well is, let me just change my sharing option to, actually, let's do the full screen. I want to show you the demo of the problem that I just described. So this is kind of how the development process looks in a nutshell. So we start with the P4 program, of course. First, what we need to do is to write our P4 program, assuming that we have a compiler that can automate the rest of the work for us, which will make the development process as easy as a few minutes to a few hours of work. So we have our table called Rocky Mirror. It matches on destination IP and BTH partition key. The action for this table supported is do mirror, and do mirror accepts a single parameter of session ID passed to built-in action mirror, and for some debugging purposes, a counter, as usual. That's how we usually verify the application to be working. So now let's compile it. So assuming that compiler has most of the integration into the Sonic stack, and I believe these kinds of compilers and tools can provide up to 100% integration, so nothing from the user will be required. Like you can see here, SAI APIs are auto-generated, which I'm going to show you in a minute. So what we have is a bunch of SAI APIs for our table to program our entries. So you can see in here is our action mirror. We can select our action. We have destination IP key. We have partition key from BTH header, and of course our session ID. So we won't waste resources. Just use what Sonic already has. and the APIs for creating and removing entries, and all the boilerplate code, everything created for us, so we don't need to do nothing. So next step that I'm going to pretty much skip is packaging all our software into a container. So I believe, again, this could be 100% automated, but I'm going to skip that because it still takes some time. So next we are going to see how this application is installed in Sonic, and pretty much nothing should be done from the image perspective. The main SyncD instance and work agent are running in parallel. So assuming that the hardware allows that, we can do dynamic entry programming with zero data plane disruption. So this is what I'm doing right now. So just to be sure nothing is installed from our demo image, we have a clean running Sonic. From configuration point of view, what we have is a pre-created mirror session. That's what we are going to use from work agent. So this is another benefit. We don't need to write all the code from scratch. Some things can be reused, but at the same time, things that work agent is not aware of, we can do on our own. And we don't even need to follow the Sonic release cycle to add new features. It could be done later on. So what you can see here is that I'm using the vendor-specific API to vendor-specific script to dump all the policies created. So right now, all the tables are all the ACL tables are empty, user-defined policies. So let's try to configure our own. So first, what we do, we install our extension. So it was preloaded to the registry, so I can easily grab it and download and install on the switch. So we don't have it running right now, but when we will install. So what happens here is just a few things. Compatible Docker image is loaded onto the switch, and based on all the metadata contained in that image, everything else will be auto-generated. So first thing first, we load the Docker image. So we have it, we have the file system. Next, installing the auto-generated CLI, auto-generating systemd service, and you can see another instance of syncd has already started. So let's move on. Okay, so second fragment will program the entry into the ASIC following all the Sonic conventions. So we install our entry using auto-generated CLI into the config DB, and I will show you how it will be reflected onto the ASIC DB. So it was installed. Now we can check what is going on the vendor specific script to see the actual policies installed, to see that it was programmed into hardware. So we have our policy created, the destination IP specified, partition key. This is something that Sonic does not know how to deal with, but we taught him right now. And the action to mirror with our session pre-created. So how it looks in the ASIC DB after all of that had been done. What we have is two things. First thing is the standard mirror session, you can see row number 2. It is in the ASIC. You can notice it is in the ASIC state table owned by the main instance of syncd. But our new policy rule is, so that this is the mirror session itself. But our new policy rule is, as you can see in the row number 1, it is in a different ASIC state table called ASIC state Rocky Everflow, managed by the other syncd instance. So this is our Everflow session. Sorry for the duplication of the IP addresses, but I noticed it a bit late. And this is what we created on our own that Sonic did not know how to deal with before. We have our action mirror, partition key, value in decimal. We have destination IP and the session ID, object ID over here, row number 8. It is taken from the others in the instance and reference. So yeah, and another interesting point that I mentioned here, the switch, when we create a subsequent switch instance, we do not trigger initialization or reset. We said that init switch should be false in our control application. So this is how I think it should work. So this is a nice template to extending Sonic in all possible ways, either going as extreme as introducing new protocols and new SI APIs, but also introducing features using standard SI APIs. It's also possible. It doesn't have to be a part of Orc Agent. We can think of it as distributing the Orc Agent operation. So call to action from our side is 3 things. First one is please follow the Sonic application extension proposal. Recently, there was a first review in the community. We will be following that with the next phases of a deeper integration. Right now, we're talking about installation and definition of the Docker compatible image. Next will be actually programming SI, which is very interesting. FlexSci, this is something contributed by our company a long time ago. I think this is also something interesting to be studied and to be followed by every other vendor. From the developer's point of view, we are encouraging everyone to make Sonic open to extensions, make it rather a tool instead of a solution. And if you are planning to bring a new feature, which is maybe not that standard, it's not something like enhancement to FRR or something like that. If it's like telemetry, something not well standardized. So please plan your feature as extension if possible, so it will not overburden the Sonic image. It will make it lightweight and will not require as much attention from the Sonic community, and it will be easier for you because it will not require to fit into the release schedule as well. So on that, thank you everyone, and we have 3 minutes for questions if there are any.
Just a reminder, if you have questions, please type it into the chat function within the web tool.
Yeah, thanks, Marianne. Yeah. Any questions?
Okay,